Thanks for coming, everybody. I'm Guy. I'm a PhD student at Columbia. And the talk today is going to be about what artificial intelligence and economics can teach each other. Okay. There we go. Wait. Anyways, okay. So I'm an economics PhD student, but I did my undergrad actually across the river at BU in computer science. This talk is going to be a little different from most of the ones today. It's going to be, going through a lot of intellectual history and kind of giving a bird's eye view of the way that I view progress in artificial intelligence and the study of economic decision making. I hope to convince you that we share fundamentally similar problems, but we kind of have different ways of thinking about them. And at the end, I'm going to kind of present some preliminary work that's at the intersection of CS more broadly and economic decision making. And so, where is this not working? Okay. So the starting point that I want to start from is kind of, Herbert Simon is this figure in economics who's kind of been a pioneer in the study of bounded rationality. And so he's really famous in economics. He won the Nobel Prize, and most of his work is kind of applying models where individuals aren't perfectly rational and applying them in different market settings. And as I'm sure most people here know, wait, why is this not? Okay, sorry about this slide. Something weird happened with this computer. So Simon kind of viewed understanding how humans solve problems as being a blueprint for how to design computer programs that would solve these same problems, right? So he kind of took the way that humans would solve these problems as a model for how computers would actually solve them. And thinking about how to solve a problem in a computer could actually serve as a model for how an individual would actually solve that problem. However, since Simon, there's actually been very little people that actually work at this intersection between, studying economics, specifically decision-making, and artificial intelligence. And so first, I kind of want to take you on a brief intellectual history of the study of economic decision-making. So, okay. So in the beginning of neoclassical economics, kind of the big idea was kind of using some sort of revealed preference argument, right? So it kind of treated the decision-maker as a black box. So take the following decision problem, right? You're choosing between a grapefruit, an orange, and a kiwi. Right? And so, the classic models in economics would basically just care about which thing you actually would pick. So for instance, if I would choose the orange, all that means is that, I prefer the orange to the grapefruit and the orange to the kiwi. It didn't matter what decision-making process I was engaging in when I actually was trying to figure out which thing to do. All that matters was what I revealed. And if you took this to even more complicated problems, basically we would always just assume that, people were perfectly rational and that the decisions that they made were optimal decisions. And we were writing down models that were kind of as if they were solving some potentially very hard problem. So the problem with this is that, so this was the dominant paradigm in economics for almost 40 years. And it took a lot of work by people like Richard Thaler and Daniel Kahneman to kind of empirically show that there was many documented cases when there was substantial deviations from supposedly rational behavior. Right, so Richard Thaler had this very nice set of papers in the Journal of Economic Perspectives that were just kind of documenting these anomalies, right? And there's a lot of potential reasons that one could think that kind of drives this behavior, but the biggest idea was kind of that many choices in environments that individuals actually act in are complicated, right? And so it took people a while to kind of relax this notion of people are acting optimally to they're kind of acting optimally. Subject to the fact that they're potentially cognitively bounded, right? And so most of the work that was done in the 80s and 90s in economics was very empirical, right? So they put people in a bunch of different situations, and they showed that the models that we had were just systematically failing at predicting behavior. But the one problem that kind of happened was that we just had, we had all these empirical phenomena, and we had a bazillion different models for explaining this kind of behavior. And so before I continue, just a brief digression about what do economists really do? So we mainly write down models, right? And what are models? Models kind of take some economic phenomena that we observe in the world. We write down a very simple mathematical model that kind of clearly spells out the assumptions of, what assumption we're making on the decision maker, what assumptions we're making on how they act, and then we kind of observe the implications. Sorry. Approximate rationality? So it means, in some sense, it means you're potentially rational with respect to the cognitive constraints that you have, right? So for instance, if you're playing chess or something, right, there's an in principle rational thing to do. You could just play the backwards induction thing, but you know, if you assume that I don't have the computational power to actually compute that equilibrium, does that make sense? Okay. So, but I think it'll become clearer later as I discuss some more things. And so what we traditionally do is kind of, given a model, we can go back to the real world and kind of ask if in situations where it's reasonable that our assumptions should hold, our model is actually consistent with behavior, right? And the point is to not necessarily to predict behavior, but to have parsimonious models that help us understand the mechanisms behind what actually is going on, right? And so in the last 10 or 15 years, you know, we had all these different models of, you know, potential behavioral phenomena, and there was a small subset of economists that basically, you know, were churning out these models, but most of the profession wasn't really using them because it was kind of hard to choose between the models. And so there's been this, I think, relatively big idea in the last 10 to 15 years to kind of base, you know, one criteria for the model, right, is like, first off, it has to be mathematical in the sense that I can write down the exact assumptions and observe the implications. It has to be behavioral in the sense that it can be used to explain some behavior. But the big idea now is kind of that the models you write down should also be consistent with how people actually make decisions, right? So the computational processes that people actually do when they're, you know, in various environments and what actually goes on in the brain. And most of these models kind of would bring in insights and models from computational neuroscience to better microfound economic models. And so the way you should view this is kind of, you know, we view decision makers in the world, and we kind of try to wonder what kind of models can we write down, assuming that people are kind of doing the best that they can. But we're kind of trying to figure out what does it mean to do the best that you can, right? And so if we actually move back over to artificial intelligence, so in the 50s there was kind of this idea that, you know, what is an intelligent thing? It just always does the right thing, right? And so one potential view is that, you know, designing an intelligent agent is the same as designing a rational agent, right? So in economics, we kind of viewed individuals as basically saying, you know, we suppose they're doing the best that they can. Whereas here, you know, we started to ask the question of what does it mean to design a rational agent? And kind of, if you start to think about this question, you kind of get similar insights that, you know, we kind of got in economics, but from a different perspective. So there's this very nice paper by Stuart Russell on rationality and intelligence that gives the following possibility for what does it mean to design a rational intelligent agent. So the first could be perfect rationality. So it just always does the best possible thing in a given context, right? So for instance, you could take the example of chess, right? So there's a unique optimal thing to do. So an intelligent agent would be the one that just always does the right thing, right? But it might be very hard, for instance, to actually write the optimal program, right? The second is kind of, you know, the first is kind of infeasible for the same reason that, you know, it would be great if we could get there, but it seems that there are computational problems. The second is in a similar notion, right? So it's calculative rationality. So suppose I didn't worry about, you know, how costly it was to compute something. So for instance, in the example of chess, I could right away optimally compute the optimal strategy. As long as, you know, that thing was in principle computable, that would be what we should strive for. But that seems, again, ridiculous, because that would mean that, like, you know, even if I wrote an insanely inefficient program to play chess, that would be an intelligent system. The third is to kind of get to, you know, instead of just thinking about how good is the thing that I end up with, is take into account how much deliberation it actually takes to get there. So, I mean, the third is kind of to think about, you know, agents as engaging in some optimal meta-reasoning process to kind of find the optimal trade-off between what are computational costs and, like, decision costs and decision quality, or computational costs and decision quality. Sorry, yeah.
Isn't there a two-step process? One is understanding the mechanisms and how something works. The other is your decision and how to leverage that knowledge, make a decision. It seems it's a two-step process professionally.
Yeah. So that's in some sense the difference between 3 and 4. So on 3, you can kind of think the meta-reasoning process is I engage in that second-order process. So there's some problem I'm trying to solve, but when I'm trying to reason about, like, if you think about what does it mean to do meta-reasoning, right? So I have to think about, I'm going to take this computation, it's going to give me, you know, an expectation, this amount of extra value. and then I have to reason about what the costs of that are as well, right? And so there, you know, it's this two-step thing of one, I'm thinking over the space of all possible programs that I could use. Yeah. And so the fourth kind of is a little bit weaker, but I mean, Russell tends to think it's the right way to go, and I kind of agree with him, is that instead of supposing that, you know, the agent kind of is actively engaging in this meta-reasoning process, which might arguably be just as hard as the actual problem that you're solving, and potentially even harder because of what you pointed out, which is that there's this two-step optimization problem, right? So in general, we kind of want to design agents that, you know, given the fact that they're under these computational constraints, they kind of do the best that they can under these computational constraints. And so, you know, when designing agents, kind of, it's important to think about the computational costs. And kind of, it kind of positioned to move towards thinking about these sort of optimality, taking into account the fact that we have computational costs. And so then, you know, the latest trend is if you go to like literally every other talk in this conference, you know, people are basically very interested in deep learning, and there's been a lot of interdisciplinary work in recent years between computational neuroscience and computer scientists, and at least the way that I view it is kind of, you can view neuroscientists as kind of, you know, they work on, in some sense, reverse engineering the brain, and how it kind of does certain processes, such as vision or, you know, playing Go or whatever you want. And, you know, computer scientists kind of try to take the main ideas from these and kind of put them in implementable models and try to extend upon them. And I think like the classical example of this is, you know, the whole story behind convolutional nets and the visual cortex, right? So, I mean, I'm sure most people know this, but like, you know, most of the ideas behind COMNETs come from these Uber and Weisel studies of how cats actually see. Okay, so let's step back for a second before we go on. So how are these fields of study the same? So at around the same time, they kind of both started for this conceptual goal of basically, you know, I want to design an agent that, so in the field of artificial intelligence, we kind of said we want to design these agents that always do the right thing. As economists, we kind of just said we're going to assume that, you know, when we observe behavior of individuals, they're always kind of doing the right thing. They both slowly recognized that in order to have realistic models, computational constraints kind of needed to be taken into account. And so it was no longer just, you know, doing the optimal thing, but doing the optimal thing taking into explicit consideration computational costs. And then the third was kind of, they both recently begun to draw inspiration from neuroscience. And, you know, we developed theoretical models of choice that have foundations in how the brain processes information and kind of use this to select between our models. You know, artificial intelligence basically uses these as inspiration for how one might engineer agents to perform these processes. But at the same time, they're very different, right? So like if you think about what we try to do, we aim for these very simple parsimonious stylized models that might not actually do a good job of prediction, right? We kind of aim to kind of understand the fundamental mechanisms of what drives explained behavior that we see. Whereas in artificial intelligence, you kind of have that people are more likely to, you know, we kind of have these more complex models that aim for, you know, actually approximating human level behavior. A lot of our simple models, you know, in prediction exercises actually do rather poorly. But, you know, we kind of aim for parsimony and understanding as opposed to, you know, approximating human level behavior. And so what I'm going to do the rest of this talk is I'm going to very briefly, you know, throw out a random idea that I had about how, you know, thinking how these economic models can kind of help artificial intelligence. And then the rest of it is going to kind of be about some work that I've done that's somewhat at the intersection of these. So, you know, there's this big problem of interpretability. And so, you know, one thing one could think of is, you know, you could start from some observed behaviors of what do we observe the individuals actually do. And then, you know, the second step here is kind of, you know, neuroscientists kind of understanding what's the biological basis for this behavior, what goes on in the brain that actually drives this behavior. And I kind of view most people as kind of jumping from 2 to 5, right? So we kind of have the high level idea of what's going on in the brain. And then we kind of say, okay, well, I can kind of build an architecture that's somewhat similar to that. One possible thing you could do is, you know, as economists, we really care about, you know, understanding the mechanisms of choice. And so you could take a particular domain, kind of work through the mechanics of all the tooling that we have in terms of building these parsimonious models that try to capture the fundamental aspects of, you know, what's going on. And then, you know, empirically kind of iteratively test at how this does at explaining behavior, and then use the insights that you gain from there to guide how you design neural networks, and that kind of potentially can help with understanding, but that's just a random idea. Okay. So the rest of this talk is kind of going to take Russell's notion of bounded optimality and kind of apply it to understanding some of the puzzles that we kind of have in behavioral economics. So so in the empirical work in the 80s and 90s, we kind of identified that individuals use these heuristics very often, in the sense that basically when they're given a problem, they might do something that's very seems very stupid, but ends up doing reasonably well most of the time. And most of the people in our field, at least, used to think that these are just people are being irrational, but that maybe it makes sense in the face of computational costs. And so there's been some pretty good recent work in computational cognitive science by I think Josh Tenenbaum at MIT and Tom Griffiths and these guys at Michigan, Lewis, Howes, and Singh, that kind of focus on applying this idea of bounded optimality to human decision making. And the main idea of it is basically that you can actually use some of the models that Stuart Russell and a lot of his co-authors worked on in the 90s to kind of rationalize the heuristics, or like the programs that people in some sense commit to when they make decisions. I'm going to leave for the future, the possible connection between neuroeconomics and the recent trend in neuroscience-inspired artificially intelligent agents. And so my work is kind of really, I kind of took this as a starting point, and there's this very understudied question of like, what are the actual computational costs that humans face, right? So if we're supposing that people are committing to algorithms to solve particular problems, and they're trading off decision quality and computational costs, what are the computational costs that humans face, and what kind of algorithms can people actually implement? So I ran a very simple experiment with some very, very naive hypotheses, just to kind of play around with this topic. So this is a lab experiment that I ran back at Columbia. It's very simple. So I just take two tasks that have different asymptotic computational complexities. The first is basically you have a list of numbers. You just want to find the single number in a list that's bigger than 750. And the second is kind of, you have a sorted list, and you kind of want to find three numbers that sum to 0. So these are very simple tasks to explain, that the subjects are taught the best algorithm and kind of get some practice runs with it, and they're only rewarded for the correct answer, so that you're not incentivized to do some sort of silly stuff. And additionally, kind of track the computational process employed by the subjects to kind of ensure that they're actually following the algorithms that we tell them to do. Okay, so this is just the interface. It's very simple, so I can you kind of hover over things to reveal them. This is the other task. You can like pin 3 things down at a time, and you go through these things and input the numbers. And so I'm just gonna, because I'm running a little bit low on time, I'm just gonna really go over this pretty quickly. So all I really cared about was kind of, the one thing I'm gonna present here is kind of looking at the computational time. So I made a very naive assumption, and I basically said I'm gonna take a stand about, what computational model, people could potentially be using, and kind of calibrated the number of steps so that basically, there was a set of tasks, and basically, in principle, the task should have taken, 25 computational steps, 50, et cetera, and just kind of saw how would response times actually scale. And so this is kind of, I thought this was kind of striking. So like, for instance, on very simple tasks, so, if you go up to, n equals 250, it would take people, roughly between like 3 or 4 minutes to actually execute these things. And there was some insane outliers, like there were some people that spent like an hour on some of these tasks. And the results are kind of, there's this question of, okay, so suppose that, individuals are selecting algorithms to optimally trade off decision quality and computational costs. So which ones are actually feasible? And so traditionally, pulling some stuff from cognitive science, people utilize this, this classic distinction between P versus NP. And it's interesting to ask, why is this the distinction that we usually use for, feasibility, besides the fact that, besides the nice mathematical properties of this problem. And so if you look, kind of, it's like, you know, most problems that we know in P are like linear, quadratic, or cubic, and most NP-complete problems are exponential, and, you know, in general it's C to the n, but most things that we know are 2 to the n. And the classic distinction in computer science comes from the fact that for, you know, empirically, for reasonable input sizes, problems in P produce reasonable computation times. And, you know, this is something I'm going to be exploring in the future, but basically, you know, in our quadratic task and for our linear task, like, people will take insane amounts of time for these particular tasks. And yeah, it might point to the fact that the set of tractable algorithms is more nuanced than P versus NP. And so, you know, if we want to really think about this notion of, you know, humans as being boundedly optimal, then, you know, it's important to realize that, you know, somewhat obvious things that the cost of computations depends in an important qualitative way on input size, in a way that, you know, we don't really have to worry about in computer science. And I didn't report some of these figures here, but failure rates grow really quickly, right? The inability for individuals to actually implement algorithms grows very fast. And so, you know, we might need to rethink about, you know, if we want to think in this general framework, that there's a much smaller subset of algorithms that people can actually implement that are traditionally considered in algorithm design, and, you know, thinking about what are the consequences. Okay, and so I think I'm out of time, so I'm just going to conclude. So, you know, if you walk away with anything from this talk, I hope I somewhat convince you that, you know, artificial intelligence and the study of economic decision making have at their core like similar ideals and starting points. There's basically no communication between the fields, even though we both at the same time talk to intermediary disciplines such as cognitive science and neuroscience, but for some reason don't talk to each other. And so I think that there's probably a lot of interesting room for collaboration between the fields. So, thanks. Yeah.
I've heard from a number of people that the way in which an algorithm makes a decision is entirely different from the way people do it. And that's part of what you're including?
What do you mean? You mean the algorithm that you would commit to, in some sense?
Maybe two shapes. The way people do it,
Yeah.
I've heard, it's quite different.
Yeah, so I mean, there's a number of tasks where, you know, for instance, we observe that, you know, human performance somewhat trumps what we can, you know, what we're currently capable of. And there's a genuine question as to what computational mechanisms people are doing. So for instance, you know, this whole transfer learning stuff between, you know, like, if you give a kid a game, they can learn it really quickly, whereas we need to train something for an insane number of hours. But I think that it's a very broad question. It's hard to say. There's some things where we do things that are very similar, and there's other things where, you know, things are potentially different. And one possible explanation for this is just that the model of computation that we're using is different in some ways, right? So for instance, in my tasks, like if you were to implement a computer to do these couple of tasks, like you wouldn't have failure rates, right? Whereas, you know, I didn't report them here, but like, you know, like for these very simple problems, people fail like 30 to 40% of the time, right? And it could just be that there's fundamental differences in the computational models of like what's going on when you're on a computer and what's actually going on when you process information. I don't take a stand on what that particularly is, but it's something to be thinking about.
But it sounded as if earlier in time people wanted to use neuroscience as a guide for computers. So.
Yeah. So I mean, for instance, if you think of Herbert Simon's work, and most of his stuff, like I said in the beginning, was based on that same notion, right? That basically, you know, understanding how humans would solve a problem could be a blueprint for how computers solve a problem. But that's just one particular way of looking at things, right? In principle, I can program a computer to do whatever I really want, right? So one blueprint could be what people do, but there are potentially, obviously, better things to be done. All right. Yeah.
What are some potential industry-level applications for AI?
I don't know. That's a good question. I mean, in general, I mean, there's a lot of people thinking about bringing in. I don't know what these guys do, but there are a lot of people in behavioral economics that try to work into putting these things into practice. In terms of the particular way incorporating artificial intelligence, I don't know. I have to think about it for a bit. I can't think of anything off the top of my head. All right, any other questions? No? Okay, cool, thanks.